To use a three-phase machine in a building with only one-phase power, you'll need to convert the power supply. This involves two main steps: phase conversion and voltage adjustment if necessary. Firstly, you'll need to convert the one-phase power to three-phase power. Two common types of phase converters are available: static and rotary. Static phase converters use electronic components to create a synthetic third phase. They are generally more expensive but offer better efficiency and reliability. Rotary phase converters, on the other hand, employ a rotating motor to generate the third phase. They tend to be less expensive upfront but can be less efficient and may produce more noise and vibration. For a 50 amps machine, select a phase converter with a capacity of at least 60 amps to provide a sufficient safety margin and handle potential surge currents. Secondly, you might need to adjust the voltage. In this case, the machine requires 220 volts, but the building provides 240 volts. A step-down transformer is not needed as one mentioned here. To address this discrepancy, a step-up transformer should not be needed, as one here mentions, but depending on the equipment, could be with a primary voltage of 240 volts and a secondary voltage of 220 volts will fix it. The transformer's power rating should match or exceed the machine's current draw, typically around 50 amps. After obtaining the phase converter and step-up transformer, the next step is wiring. The phase converter and transformer are wired in series between the building's electrical panel and the machine. The phase converter is connected to the one-phase line, and the step-up transformer is connected between the phase converter and the machine, if one is even needed. Several products are available from different suppliers. For a static phase converter, consider Phase Perfect RT24, which has a 60 amps capacity. If a rotary phase converter is preferred, the Marathon PQ2F-68, also with a 60 amps capacity, is a suitable option. For the voltage step-up transformer, the Stanger P-6181, rated at 50 amps, 240 volts to 220 volts, is a viable choice if it's required. These conversions and corrections will involve some costs. A phase converter may range from $1,500 to $3,000, while a step-up transformer could cost between $500 and $1,000. Wiring and installation expenses can add another $500 to $1,000, bringing the total estimated cost to $2,500 to $5,000. However, it is essential to consult with a qualified electrician for proper sizing, installation, and ensuring the safety of the equipment. A phase converter transforms single-phase alternating current (AC) power into three-phase AC power. Single-phase power, commonly found in residential and light commercial settings, delivers power through two wires, a hot wire and a neutral wire. In contrast, three-phase power, typically used in industrial and heavy commercial applications, utilizes three hot wires, each carrying an AC signal that is 120 electrical degrees apart. This configuration provides a more consistent and efficient power delivery, making it suitable for high-power equipment like large motors and machinery. The phase converter bridges this gap, enabling the operation of three-phase equipment from a single-phase source. There are primarily two types of phase converters: rotary and static. Rotary phase converters, also known as rotating phase converters, employ an induction motor generator set to produce the three-phase power. The single-phase power drives a motor, which in turn rotates a three-phase generator. The generator then outputs the required three-phase power. These converters provide a balanced three-phase output and are suitable for running multiple loads simultaneously. However, they are generally more expensive, larger, and require more maintenance than static converters. Static phase converters, on the other hand, use capacitors and other electrical components to create a synthetic third phase. They are simpler in design, more compact, and less expensive than rotary converters. However, they typically provide a less balanced three-phase output, and their performance can be sensitive to load variations. Static converters are often used for applications where only one or a few loads need to be powered. The selection between a rotary and static phase converter depends on the specific application requirements, including the power demand, load characteristics, budget, and space constraints. Rotary converters are generally preferred for applications requiring balanced three-phase power and the ability to handle multiple loads, while static converters are suitable for simpler applications with less demanding power requirements. Key specifications for selecting a phase converter include the input voltage and frequency, which should match the available single-phase power supply. The output voltage and frequency should match the requirements of the three-phase equipment. The power rating, measured in horsepower, HP, or kilovolt amperes, kV amps, should be sufficient to handle the equipment's power demand, with a safety margin to accommodate startup surges. Also, the load capacity indicates the maximum load that the converter can handle. Consider the type of load being powered, as some loads, such as motors, require higher starting currents. The efficiency of the phase converter is an important factor, especially for continuous operation. A higher efficiency translates to lower energy costs and reduced heat generation. Additional features to consider include overload protection, voltage regulation, and the ability to handle unbalanced loads. Proper installation of a phase converter is crucial for ensuring its safe and reliable operation. It is recommended to consult with a qualified electrician to perform the installation. The converter should be installed in a well-ventilated area to prevent overheating. The input and output wiring should be properly sized and protected by appropriate circuit breakers or fuses. Grounding is essential for safety and should be done in accordance with local electrical codes. Regular maintenance is necessary to keep the phase converter in good working condition. This includes checking the wiring connections, cleaning the unit to remove dust and debris, and inspecting the capacitors and other components for signs of wear or damage. For rotary converters, the motor and generator bearings should be lubricated periodically. It's important to monitor the converter's performance regularly, checking for any unusual noises, vibrations, or overheating. If any issues are detected, they should be addressed promptly to prevent further damage. Phase converters are widely used in various industries and applications where three-phase power is not readily available. These include farms, workshops, small businesses, and residential settings. They enable the use of three-phase equipment such as welders, compressors, pumps, and machine tools in locations with only single-phase power. Phase conversion is a practical and cost-effective solution for expanding the capabilities of existing electrical systems and accommodating the power requirements of diverse equipment. A transformer is a passive electrical device that transfers electrical energy from one circuit to another through electromagnetic induction. It is one of the most fundamental and ubiquitous components in electrical power systems, enabling the efficient transmission and distribution of electricity over long distances. Transformers are used to increase or decrease voltage levels, isolate circuits, and match impedances. The basic principle of operation is based on Faraday's law of electromagnetic induction. A transformer consists of two or more coils of wire, cold windings, electrically isolated but magnetically linked. The primary winding is connected to the source of alternating current, AC, voltage, and the secondary winding is connected to the load. When an alternating current flows through the primary winding, it creates a time-varying magnetic flux in the core of the transformer. This magnetic flux induces an alternating voltage in the secondary winding. The ratio of the number of turns in the primary winding to the number of turns in the secondary winding determines the voltage transformation ratio. A step-up transformer has more turns in the secondary winding than in the primary winding, resulting in a higher secondary voltage. Conversely, a step-down transformer has fewer turns in the secondary winding than in the primary winding, resulting in a lower secondary voltage. The core of the transformer is typically made of laminated silicon steel to minimize energy losses due to eddy currents. Eddy currents are circulating currents induced in the core material by the changing magnetic flux. These currents dissipate energy in the form of heat, reducing the transformer's efficiency. Lamination reduces the magnitude of eddy currents by increasing the resistance of the core material to their flow. Transformers are classified based on various factors, including their construction, application, and insulation type. Based on construction, transformers are classified as core type or shell type. In a core type transformer, the windings surround the core, while in a shell type transformer, the core surrounds the windings. Based on application, transformers are classified as power transformers, distribution transformers, instrument transformers, and audio transformers. Power transformers are used in high-power applications, such as power generation and transmission. Distribution transformers are used to step down voltage for local distribution to residential and commercial customers. Instrument transformers are used to measure high voltages and currents safely. Audio transformers are used in audio equipment for impedance matching and signal isolation. Based on insulation type, transformers are classified as oil-filled transformers and dry-type transformers. Oil-filled transformers use oil as an insulating and cooling medium, while dry-type transformers use air or other gases as the insulating medium. Oil-filled transformers are typically used in high-power applications, while dry-type transformers are used in indoor applications where fire hazards are a concern. Key specifications for selecting a transformer include the voltage rating, power rating, frequency rating, and impedance. The voltage rating indicates the maximum voltage that the transformer can handle. The power rating, measured in kilovolt amperes, kvolt amps, or megawatts, indicates the maximum power that the transformer can deliver. The frequency rating indicates the frequency of the AC voltage for which the transformer is designed. The impedance is a measure of the transformer's opposition to the flow of alternating current and is important for determining the transformer's performance under load conditions. Additional features to consider include the transformer's efficiency, voltage regulation, and insulation class. The efficiency indicates the percentage of input power that is delivered to the load. Voltage regulation is a measure of the change in secondary voltage from no load to full load conditions. The insulation class indicates the maximum operating temperature of the transformer's insulation. Proper installation of a transformer is crucial for ensuring its safe and reliable operation. It is recommended to consult with a qualified electrician to perform the installation. The transformer should be installed in a well-ventilated area to prevent overheating. The input and output wiring should be properly sized and protected by appropriate circuit breakers or fuses. Grounding is essential for safety and should be done in accordance with local electrical codes. Regular maintenance is necessary to keep the transformer in good working condition. This includes checking the oil level in oil-filled transformers, inspecting the bushings and connections for signs of wear or damage, and cleaning the unit to remove dust and debris. It's important to monitor the transformer's performance regularly, checking for any unusual noises, vibrations, or overheating. If any issues are detected, they should be addressed promptly to prevent further damage. Transformers are essential components in electrical power systems, enabling the efficient and reliable transmission and distribution of electricity. They are used in a wide range of applications, from power generation to consumer electronics. A qualified electrician plays a crucial role in ensuring the safe and effective integration of electrical equipment, such as phase converters and transformers, into existing electrical systems. Their expertise is essential for selecting the appropriate equipment, ensuring proper installation, and maintaining the system's long-term reliability and safety. Firstly, a qualified electrician possesses the knowledge and skills to assess the specific electrical needs of a building or facility. This involves evaluating the existing electrical infrastructure, determining the power requirements of the equipment to be installed, and identifying any potential safety hazards. Based on this assessment, the electrician can recommend the appropriate size and type of phase converter or transformer to meet the specific needs of the application. Secondly, proper installation is critical for ensuring the safe and reliable operation of electrical equipment. A qualified electrician is trained to install phase converters and transformers in accordance with local electrical codes and industry best practices. This includes ensuring proper wiring, grounding, and overcurrent protection. A correct installation can lead to electrical hazards such as short circuits, overloads, and electrical shocks. Thirdly, electrical codes and regulations are constantly evolving to ensure safety and prevent electrical hazards. A qualified electrician stays up to date with the latest codes and regulations and ensures that all electrical work complies with these standards. This includes obtaining the necessary permits and inspections to ensure that the installation meets all applicable requirements. Furthermore, a qualified electrician can provide ongoing maintenance and repair services to ensure the long-term reliability of electrical equipment. This includes routine inspections, testing, and repairs to prevent potential problems and extend the lifespan of the equipment. Regular maintenance can also help to identify and address any safety hazards before they cause harm. The importance of consulting with a qualified electrician cannot be overstated. Electrical work can be dangerous, and incorrect installation or maintenance can have serious consequences. By entrusting electrical work to a qualified professional, you can ensure the safety of your property and its occupants, as well as the reliability of your electrical system. In addition to the safety and technical aspects, a qualified electrician can also provide valuable advice on energy efficiency and cost savings. They can recommend energy-efficient equipment and practices to reduce energy consumption and lower electricity bills. They can also help to identify and address any energy waste in the system. Choosing a qualified electrician involves verifying their credentials, checking their experience and references, and ensuring that they are licensed and insured. It's also important to communicate your specific needs and expectations clearly to the electrician and to obtain a written estimate before any work begins. By taking these steps, you can ensure that you are working with a competent and trustworthy professional who can provide the electrical services you need. Phase converters and transformers are essential components in many electrical systems, and their proper selection, installation, and maintenance are crucial for ensuring safety, reliability, and efficiency. Consulting with a qualified electrician is the best way to ensure that these components are integrated seamlessly into your electrical system and that they meet your specific needs and requirements. The selection of a phase converter depends on several factors, including the type of load, the power requirements, and the available input voltage. The load type refers to the type of equipment that will be powered by the phase converter. Some loads, such as motors, require a high starting current, while others, such as resistive heaters, have a more constant current draw. The power requirements refer to the amount of power that the load needs to operate. This is typically measured in horsepower, HP, or kilowatts. The available input voltage refers to the voltage of the single-phase power supply. This is typically 120 volts or 240 volts in residential settings and can be higher in commercial or industrial settings. Once these factors are determined, the appropriate phase converter can be selected. There are two main types of phase converters: static and rotary. Static phase converters use capacitors to create a synthetic third phase. They are typically less expensive than rotary phase converters but are not as efficient and can only handle light loads. Rotary phase converters use a motor generator set to create the third phase. They are more expensive than static phase converters but are more efficient and can handle heavier loads. The choice between a static and rotary phase converter depends on the specific application. For light loads and occasional use, a static phase converter may be sufficient. For heavy loads and continuous use, a rotary phase converter is recommended. The installation of a phase converter should be performed by a qualified electrician. The installation process involves connecting the phase converter to the single-phase power supply and the three-phase load. Proper wiring, grounding, and overcurrent protection are essential for safety. Regular maintenance is necessary to keep the phase converter in good working condition. This includes checking the wiring connections, cleaning the unit, and inspecting the capacitors or motor generator set for wear or damage. A transformer is a device that transfers electrical energy from one circuit to another through electromagnetic induction. Transformers are used to step up or step down voltage levels, isolate circuits, and match impedances. The selection of a transformer depends on several factors, including the input voltage, output voltage, and power requirements. The input voltage refers to the voltage of the power supply that will be connected to the transformer. The output voltage refers to the voltage that the transformer will deliver to the load. The power requirements refer to the amount of power that the load needs to operate. This is typically measured in kilovolt amperes, kvolt amps, or kilowatts. There are several types of transformers available, including step-up transformers, step-down transformers, isolation transformers, and auto transformers. Step-up transformers increase the voltage from the input to the output. Step-down transformers decrease the voltage from the input to the output. Isolation transformers provide electrical isolation between the input and output circuits. Auto transformers use a single winding for both the input and output circuits. The choice of transformer depends on the specific application. For stepping up voltage, a step-up transformer is used. For stepping down voltage, a step-down transformer is used. For providing electrical isolation, an isolation transformer is used. For applications where voltage needs to be adjusted slightly, an auto transformer may be used. The installation of a transformer should be performed by a qualified electrician. The installation process involves connecting the transformer to the power supply and the load. Proper wiring, grounding, and overcurrent protection are essential for safety. Regular maintenance is necessary to keep the transformer in good working condition. This includes checking the wiring connections, cleaning the unit, and inspecting the windings and core for damage. The selection of the appropriate phase converter or transformer is crucial for ensuring the safe and reliable operation of electrical equipment. Consulting with a qualified electrician is highly recommended to ensure that the equipment is properly sized, installed, and maintained. The electrician can assess the specific needs of the application and recommend the best solution for the situation. They can also perform the installation and maintenance work to ensure that the equipment operates safely and efficiently. By following these guidelines, you can ensure that your electrical equipment operates safely and reliably. Remember to always consult with a qualified electrician for any electrical work.